On behalf of BN Ministry of Technology and the committee of this STTP, I welcome all the participants and our today's expert, Dr. Santanu Bandyopadhyay, sir. Uh, Dr. Santanu Bandyopadhyay, sir, is currently Praj Industries Chair Professor at Department of Energy, Science and Engineering at the Indian Institute of Technology, Bombay. He obtained his BTech in Energy Engineering from IIT Kharagpur in 1992 and MTech and PhD in Energy Systems Engineering from IIT Bombay in 1995 and 1999 respectively. His research interest includes process integration, pinch analysis, industrial energy conservation, modeling and simulation of energy systems, design and optimization of renewable energy systems, etc. Since 1994, Professor Bandyopadhyay has been associated with and contributed towards various developmental, industrial, and research activities involving different structured approaches to process synthesis, energy integrations, and conservation, as well as renewable energy system design. Prior to joining IIT Bombay, he worked for Messrs. Engineers India Limited, New Delhi. He was one of the section editors for the Elsevier project, Encyclopedia of Sustainable Technologies. He is currently one of the editor-in-chief for Process Integrations and Optimization for Sustainability, Springer Nature Journal, as well as associate editor for Journal of Cleaner Productions, Elsevier, and Cleaner Technologies and Environmental Policy, Spring Nature, South African Journal of Chemical Engineering, Elsevier, and uh, Transactions of the Indian National Academy of Engineers, Springer Nature. He is a fellow of the Indian National Association of Engineering, INA. So, with this great profile, he has been serving at many platforms, whether technologicals or we are having the blessings to hear such a great professor from IIT Bombay. So I will not waste my time, and I will hand over this session to Dr. Santanu sir, who is going to present his topic on industrial energy conservation, a pinch analysis approach. Dr. Santanu sir, please.
Thank you, Groje Badrakia, for a nice presentation. Okay. Let me first share my screen. Is it visible?
Yes, sir. Perfect.
Yes, sir.
What I'll do is I'll just put the video off so that there should not be any problem with the bandwidth. Okay, so let me start.
Yes.
Yes, sir. Is there any problem?
No, sir.
Okay. So we are going to talk today for roughly 1.5 hours on industrial energy conservations, a pinch analysis approach. So we'll be talking about pinch analysis and how energy conservation can be done, primarily thermal energy. And then we'll discuss about how pinch analysis has been extended over the last couple of decades, what different applications, and then we'll conclude the talk. And even if you have any questions in between, just please stop me and ask that question. I'll try to clarify your doubts as much as possible. So let me start with first the thank you note. I'm really thankful to BNB Institute of Technology as well as organizers of this ICT sponsored short-term training program. With special thanks to Professor Anurag Emmanuel, who actually contacted and I have been in touch with him. I'm thankful to all my collaborators internationally as well as nationally, my department, my institute, and in the last but not the least, my students, through whom actually I've learned this topic. Let's start with first about anything with the foundation. Okay, so let's look at the definition. And since last few days we are talking about energy management, let me start with the definition of management itself. So now this management term essentially means like optimal utilization of resources to meet desired objective. So what do I mean by that is whenever there are any kind of resource and how do you utilize them optimally, that and to achieve certain objectives is the management. Now, energy management term was coined in the 70s, essentially to look at the efficient utilization of energy. So energy as a resource. And so we talk about different strategies, optimizing energy systems, okay, the procedures, operational process, okay, and all of this so that we can reduce the cost. And to some extent nowadays we are talking about, can you reduce the emissions, can you go towards sustainable. So one of the techniques of energy management is process integration. I'm sure that last few days you have learned many different techniques. So I'm going to talk about process integration and a small amount or subset of this process integration called pinch analysis in little more details. So let's start with hierarchical analysis. Whenever we have to do any kind of analysis, we need to define the boundary and then we have to also define the approach. So when we start with hierarchical analysis, the first thing we decide is how we are going to take the decisions. Should it be interactive? Each step the designer has to give or operator has to give some inputs or some decisions, or the computer will take the entire call and then produce the final solution. And the other hand, we can talk about what kind of models we are going to look at, whether it will be qualitative model, more descriptive, based on experience, or it can be quantitative, which you can write down through mathematical equations. Now, if we look at the first quadrant, where we are going to talk about qualitative models or descriptive models with designer interventions, we call them basically heuristic rules, rules of thumbs, and so forth. They're simple and they are extremely helpful to take the first initial decision, initial screening process. If you go to the second quadrant where we are talking about qualitative model, but computer is taking the decision, it's knowledge-based system, rule-based automated approaches, or nowadays you can talk about, in certain cases, we are making certain measurements and making more artificial network, machine learning kind of approaches are started coming in, where some of the qualitative tools are also converted to quantitative and making a mixture of them. The third one is extremely popular among us, all the academicians, are optimization based approach, where computer will give you the solution and you are using all the mathematical equations and models to describe your system. So mathematical programming, stochastic search models, and we can talk about many. The fourth quadrant is where you have interactive decision-making process with mathematical models, is like thermodynamic methods. So exergy analysis, pinch analysis is just one of them. So now, if we look at these methods in the third and fourth quadrant, we call them process integration and optimization approach. I'll talk about very briefly about these two approaches, like optimization method as well as thermodynamic based method or conceptual methods. And then we'll try to look at more from the pinch analysis perspective. So the objective of these process integrations are to minimize the total cost, looking at the trade-off between capital investment as well as the operating cost. Then we are talking about, can we enhance the plant capacity by doing debottlenecking? Now this debottlenecking is the other side of the coin called energy conservation. So whenever you do energy conservation, what you do is you keep the production same and try to reduce the energy requirement. On the other hand, when you talk about debottlenecking, we'll keep the energy requirement same but enhance the production. So it's just the other side of the coin. Process integration are used to reduce operating problems, enhance the controllability, okay, looking at the topology. It can enhance the flexibility of the plant. It is used to minimize the undesirable emissions and aim for sustainable development. So let's look at the difference between these two techniques that we are going to talk about. One is the mathematical based optimization techniques, and I'm sure all of you are extremely familiar with them. Now, this is a very good tool to take very complex situations, like wherever you can write down the equations, probably you can take them. Okay, you can take multiple contaminants in water kind of problems. You can talk about controllability, flexibility. Extremely difficult economic situations can also be taken. Okay, it's a very good synthesis tool, especially complex systems with complex constants. However, it has certain demerits. The problem comes with is combinatorial explosion and local optimality. What do I mean by combinatorial explosion? Is like all the variables will not be continuous variables. There will be discrete variables. So that means you have to search in a discrete way to many different possible situations. And the number of variables increases, number of discrete space is going to increase significantly. So now what can be done in a continuous system where you can use some of the differential equations and differential equation based optimality conditions, it will become a little difficult for such kind of system. So it's become combinatorially explosion because number of search space or the number of points that you have to search increases rapidly. And many cases, this mathematical optimization, especially for mixed integer nonlinear optimization kind of problems, our mathematics is not developed enough that you can guarantee even local optimality. So sometimes the solution comes that is not even a local optimum. It does not provide good insight because finally what happens is it gives you a solution. You have to take it, or else you have to change it again, run that entire program, and then try to find out something happening. So, or the next best solution. It's very difficult to find out a series of solutions and then you can choose from there. Okay. And in many cases, this optimization problems can have a special structure, and this structure can be exploited and efficient algorithm can be designed. So general method or the generic methods are not capable of that. So you have to develop specific tools. Now, the conceptual approaches or the thermodynamic based methods helps in finding out the physical insight. Okay, and it produces some graphical interpretation, simplified calculation procedures, so that you can do it very quickly with a pen and paper. You can make the conclusions, you can see the problems. Because it's exploit the special structure, it can be very efficiently calculated. Okay. It recognizes the importance of setting the targets. I will come back to this maybe when we'll discuss more about the pinch analysis. And different process objective can be screened. The graphical representation is extremely strong because you can view the problems and you can take appropriate things. However, until now, it can address only simple problems with simple constants. Okay. So one of the research direction is how can we enhance and we can address some of the complex systems or complex constants. Let me give probably at this point a simple example of what is the difference between the two. Imagine a function y equals to x square, or y equals to fx equals to x square. Now we need to optimize this. We have to minimize it. I'm sure that all of you know it's a quadratic parabola. And if I use the generic tool, then I'll first differentiate with respect to x. We'll get 2x equal to 0. We'll get x equals to 0. Take the second derivative, you'll get 2. So you'll say since the second derivative is positive, then x equals to 0 is the minima. Now this is a very strong tool and it can be used in many complex situations and many kind of optimization problems. But it has to go through those steps. You have to actually differentiate and all. Now, this particular function also has certain structure. I can exploit it. I can simply say if x is a real number, x square cannot be negative. It has to be non-negative. Hence, the minimum will be at 0. X equals to 0 will be the minimum. Now, in this second approach, I'm exploiting the structure. But if you give me an arbitrary function, I may not be able to exploit that structure and I may not be able to solve. So in some case, I am exploiting the physical understanding and solving it, giving more understanding of the problems. In another case, I have a genetic method to solve it. So now, obviously, I cannot say one is better than the other, but we probably have to look into both and then try to see what we can exploit maximum. Let's start with this heat exchanger network, which is directly related with conserving thermal energy in a process heat and or the process plant. And this is also the starting point of pinch analysis. So let's take the problem definition. The problem definition says we are given certain data. Which are the data given? That a set of process streams, their inlet temperature and outlet temperatures are known, their flow rates are known, and also we know their thermodynamic properties. Now here we want to distinguish the streams as hot streams and cold streams. A hot stream is defined as whose temperature has to be reduced or where from you have to take the heat out. Okay, so I can have a hot stream at minus 10 degrees centigrade if I have to reduce its temperature to minus 20 degrees centigrade, right? And cold stream is the other way around, where temperature has to be increased or heat has to be supplied. Now, so we know their flow rates, we know their specific heats. We all should know also what are the external utilities available to heat them or to cool them. And we should know their heat exchanger cost data, okay, operating cost of the utilities. And then finally, objective is to design a network of heat exchangers. That means not one heat exchanger, but multiple heat exchangers with minimum annualized investment cost and the operating cost. So that's minimum TAC, total annualized cost. That's the problem we are going to look at. So obviously, energy comes as a second. We are not talking directly about the energy, we are talking about the cost. However, the problem that we are going to describe, we are going to look at energy as the primary things. So we are at present going to neglect the heat exchanger cost data. Okay, we are simply saying, okay, we'll calculate them later, but let us first reduce and see how much energy we can conserve. Okay, that's the way we are looking at it. So let's look at the history of this problem. Now, in the open domain, the first paper was published in 1944 by a person called Ten Borek. And this is the first known heat exchanger network related paper, but he has not called heat exchanger network. He called it bridges of heat exchangers. And so you can ask probably why in 1944 people are looking at this kind of problems. See, the refineries are already in and they are operated. There are lots of plants are operated. The focus was never on energy conservation that time. However, on capital cost. Can we reduce the capital cost? So that was the major focus in those era. So he was looking from that perspective. Then few series of paper came in 60s and primarily from the academia, Professor Westerbook, Wa, Professor Rudd, okay, and Rudd and his student Maso, and there are a few more. But essentially, they have talked about a mathematical programming approach, an optimization approach, writing down all possible combination, capturing them through superstructure, okay. And the problem, the formal problem of heat exchanger is defined by Maso and Rudd. In 1968, Professor Rudd proposed a beautiful principle. He says it's called decomposition principle. If you have a problem which is large enough and you won't be able to solve it directly, then break it into small pieces and try to solve in small ways. And we'll come back to this point. In 1971, there is an interesting thesis has been done by Hohmann, who proposed composite curves. These terms will come very soon. I am going to describe these terms, composite curves, to calculate minimum energy requirement. Okay. Unfortunately, he could not publish this paper. In fact, it was turned down twice. And later on, he published only one conference paper, and that's all. So, but since a lot of industries had taken interest in pinch analysis towards the later half of the previous century, we started asking what is the problem in 1971. So the first thing we noted is 1971 precede 1973, 1974 oil shock. So that time people are not really talking about conserving energy. Okay. And the climate change was not that big. People are not talking about fossil fuels. So first of all, when he started talking about energy conservation, people are not ready to look at it. Second problem came is in that late 60s and early 70s, people are using computer for everything. Okay. And this particular approach says you can solve a problem by pen and paper or through calculator. It's not very popular. So probably these two reasons we could find out, but we are not too sure why it has been rejected twice. Then an interesting thing happened in 1978. Bodo Lenov, a student of Professor Flower, and Dr. Umeda and his team from Japan published two papers independently, and where they have identified this heat recovery pinch point. Okay, and that's what today we call the starting point of pinch analysis. So look at one paper, Lenov and Flower came from academia, and Umeda et al. Paper came from industry, and both of them simultaneously and independently talked about this heat recovery pinch analysis. And in 1983, Lenov and Hindmarsh basically make an approach called pinch design method, how the heat exchange network can be done. And an interesting problem happens in 2001. Professor Shahanidis and his student Furman published a paper where mathematically they prove that the problem of finding out minimum TAC is an NP hard problem. Okay, so if the number of variables increases, it's becoming non-polynomial. It might take huge amount of time, and especially industrial problems will be very difficult to solve through mathematical optimization. Then basically we have to go for a sequential optimization. That means we have to look for Professor Rudd's decomposition principle. So pinch analysis is essentially looking at this decomposition principle and not try to solve the entire problem at a single go, but dividing into a small pieces and try to address them. So this is one example problem I've taken from Professor Shenoy's book. And if you look at, there's a C3 stream which comes at 20 degree. Let me put my laser pointer. Okay, now so it comes at 20 degree. It is heated up to 155 degree, goes to a reactor. The reactants are coming at 175 degree. It cooled to 45 degree, goes to a distillation column. From the top of the distillation, the distillate is coming at 40 degree. It is heated up to 112 degree and then goes out of the battery limit. Battery limit means out of the process, goes to the next process. And the bottoms of the distillation column comes out at 125. It is cooled to 65 degree and goes to a storage tank. Okay. So if you look at our definition that the temperature has to be increased for a cold stream, So we have 20 to 155. So this is a cold stream, C3, and 40 to 112, this is C4. And 175 to 45 is temperature reduced, it's a hot stream. And 125 to 65 is our another hot stream, H1 and H2. So it has two hot streams, two cold streams. These numbers are exchangers. So there is one exchanger 1, exchanger 2, exchanger 3, and exchanger 4. Exchanger 2 and 3 are process heat recovery. Okay, see, this is coming at 125, giving heat and going out at 98. This is picking up that heat. Okay, so coming at 45, going at 112. This one is coming at 20, going out at 85. Okay, and the heat is coming from cooling this H1 from 175 to 45. Now, if C3 has to go up to 155 degree centigrade, then 85 is not sufficient. We need to heat it up. So we are providing steam heating, and the duty of this exchanger is 1400. Similarly, cold water is used to reduce the temperature from 98 to 65 for H2, and it required 1320 kilowatt of cooling water. Okay. So this cooling water has been given in terms of kilowatt. Here also steam. You can always convert it based on the temperature, pressure conditions. Okay, and if you know the latent heat or heat specific heat, you can calculate in kg per hour as well. But it really doesn't matter. Now, so there is already some amount of heat exchange. Now, our objective is to answer the questions like, can we reduce the steam? Or maybe steam will remain same, but can we reduce the cooling water? Or can we reduce both? How much we can reduce? Okay. So these are the questions that we are going to answer. So that means, can we recover the heat better? So that's the energy conservation. Can we do the conservation of energy, reduce the utility requirement, save money as well? Now, that particular diagram, previous diagram, was extremely cluttered. We are going to present it in a simpler form called parallel grid representation. So here is H1, which is a steam heater. Exchanger 2, which is between H2 and C4 with a duty of 1080. Exchanger 3 is between H1 and C3 with a duty of 1300, and exchanger 4, which is a cooling water, with a duty of 1320. Okay. Now, the next important point is we try to calculate what is the mass flow rate into CP or MCP. Now, MCP can be calculated using the equation Q equals to MCP delta T, or change in temperature. So let me do it for H1. It starts from 175, goes to 45 degree. That means change in temperature is 130, and duty is 1300. So Q is 1300, delta T is 130. So what will be MCP? MCP is Q divided by delta T, 1300 divided by 130, so it will become 10. Now we can calculate similarly for H2, C3, and C4. Once we have calculated this, then we can see what can be done. Can we look at this? Can we design? So one of the approach where people have done before is to try to find out some heat exchanger. If I place here, can I shift some temperature here and there, but thereby I can save some energy. So that approach is extremely time consuming, and you do not know whether you are getting a good solution or not. So pinch analysis helps out here. So pinch analysis essentially try to look at from a thermodynamics point of view. Now, those of you with a thermal background or has gone through thermodynamics, I'm sure that all of you will agree with the statement of Professor Arnold Sommerfeld. So he said thermodynamics is a funny subject. The first time you go through it, you don't understand it all. The second time you go through it, you think you understand it. except for one or two small points. The third time you go through it, you know that you don't understand it. But by the time you are so used to it, it doesn't bother you anymore. And maybe we go there and start teaching with this confusion. Okay. But taking this on a lighter side, we are going to use this thermodynamic method and try to find out how much we can extract from it. So the first thing is, let's look at the first law, how much heat is available and how much heat is required. So H1 can give 1300 kilowatt of heat, H2 can give 2400 kilowatt of heat. Total heat available is 3700. And similarly, if I add the heat required by the cold streams, I can see that this is 3780. So now if I do not transfer the heat from the hot streams to the cold streams, that means this will be my cooling water requirement or cold utility requirement, 3700, and 3780 is the maximum hot utility requirement. Now this is definitely not looked at it because it does not talk about any energy conservation. Okay, but this is one of the limit. Okay. Now, what is the other limit that we can talk about? So maximum hot utility and maximum cold utility know for this process. Can you find out what will be absolute minimum? That will be helpful for us. So let's do some simple heat balance. So from first law of thermodynamics, we can say that energy, what is available from the hot stream, okay, and the hot utilities must be equals to the heat required by the cold stream and the cold utilities. So I can write down this equation, heat available from hot streams, and even if I required some amount of hot utility, must be equals to the heat required by the cold streams and the heat taken away by the cold utility. So if I rearrange, I'll get that QHU minus QCU, hot utility and cold utility differences, is equals to 80. Okay. So that means if I say the difference is 80, so if I take QCU equals to 0, QHU equals to 80. So minimum requirement is hot utility is 80 and cold utility is 0. But the problem is, this is from the first law of thermodynamics. I can violate the second law where it says heat can be transferred only from higher temperature to lower temperature, because here when I've written down, I have not taken the temperature information. Okay. So second law of thermodynamics says whenever I have to transfer, the minimum temperature difference should be greater than 0. Okay. It can never be negative, but we are not too sure whether we have satisfied that or not. So now we have to look back and see what can be done. Okay. So basically the problem that we look at, we'll add all the streams and produce one hot stream and one cold stream. We'll call them pseudo stream. And they have all the thermodynamic characteristics of the original streams. Okay. So we are going to add these streams, and so that we will have only one hot and one cold, and we can address the problem. Now the thing is, we are going to add them, but we are not going to mix them. Okay. So let's see how we can do it. So remember the H1 and H2 data. I'll go back quickly. H1 starts at 175, goes to 45 with a total duty of 1300. H2 starts at 125, goes to 65 with a duty of 1080 plus 1320. These are the two exchanges on these streams. So this is 2400. Okay. We'll use that. Yeah. So let's look at H1. It starts at 175 and goes up to 45, and in such a way that the horizontal distance is 1300. So this side is the heat duty and this is temperature. Okay. Now here we should point out some of the important issues. I cannot move them up and down, because as soon as I take it up or down, I am changing its temperature, but temperatures are fixed. Okay, so for representation purpose, this 45 and 175 is fixed. But I can take this stream and shift it parallel, because heat duty is always the difference between these 2 points. Okay, it's a relative measurement. It's not an absolute value of this need not be 0. I can start this one at here 2000, and as soon as this point is also moved by 2000 units, so it can be 3300. Then it's fine. It's just going to represent H1. So similarly, I can put H2. It will start at 125, goes to 65 with the duty of 2400. So again, I've started arbitrary, but this difference from here to here, this difference is 2400. Now this is H1, this is H2. Now the question is, how can I add them? So I'll add them in temperature intervals. We'll start with 45 to 65, only H1 exists. I'll take that portion. Then from 65 to 125, I'll take the heat available from H1 and H2, I'll add them. And from 125 to 175, I'll take the heat available from H1 only. And if I do that, I'll get this piecewise linear curve. Okay. So what will be the numerical values? Remember, the slope of this is 10, and this is the MCP is 10 and the MCP is 40. So from 45 to 65, delta T is 20 and the slope is 10. So 20 minus 10 is 200. So this stream is only gone up to 200. After that, 65 to 125, delta T is 60. So 60 into 10 is 600, and this is 2400. So from this point to this point is 3000. And then further we can do this as a 500, and this difference will be 500. So just to repeat graphically to see it, the lowest portion is coming from 45 to 65 portion. The mid portion is coming from the addition of the total heat available from H1 and H2. And the last portion is again coming from H1. So now this stream is called hot composite curve, which does not exist in reality. It's a pseudo stream, but it simply gives heat availability as a function of temperature. Okay, that's the hot composite curve. Similarly, we can do a cold composite curve. These are my streams C3 and C4. I add, I'll get something like this. Okay, and I call this as cold composite curve, which is heat requirement as a function of temperature. Now that means I know what is required and what is available. Let me draw both of them in the same curve. Now, when I draw them too far apart, this is the extreme. That total heat available is 3700 and total heat requirement is 3780. There is no integration because they have put really far apart. Now the question is, can I bring them very close where the solution is 80? If I bring them too close, then this difference will be 80 because this side there is no difference, 0. But the problem might come here because see here you can see little bit of green below white. That means the temperature is you are transferring heat from a low temperature to high temperature, which is not acceptable. Now, can they touch? If the delta T goes to 0, then we know there is another equation, Q equals to UA LMTD. Your LMTD goes to 0, so area goes to infinity. That means you require an infinitely large heat exchanger. The cost is infinity, makes no sense. So we definitely need some temperature difference. And this temperature difference called delta T mean or minimum approach temperature. So if I do that, then I'll draw them with a minimum approach temperature in the same graph. We'll say this is my hot composite curve, this is my cold composite curve, such that their vertical distance is a given minimum. Okay, and everywhere else it is more. You can see at this point the difference is minimum, everywhere else the vertical distance or the temperature difference is larger. Then we can see the overlap between these 2 points. And this overlap is the heat coming from the hot stream is passed to the cold stream. So this is our process to process heat recovery potential for a given delta T min. This side we have some heat available, but there is no taker. So that means I have to provide cold utility. Okay, so this is minimum hot utility and minimum cold utility. This is I requirement. There is nothing internally, so I have to transfer from the external utility. So this is my minimum hot utility. This is my minimum cold utility subject to this delta T mean, given delta T mean. The point where they come close, we call that as a pinch point. The word pinch came from distillation column where the driving force was minimum, and in distillation it used to be called pinch point, and from there it has been taken because Lenov saw that there is a similarity between these two diagrams and he called it pinch point. Okay. Now, so again I repeat, so we could add the steam and get a hot composite curve, we can get a cold composite curve, place them subject to this delta T mean given parameter, then I can find out the process to process heat recovery, minimum hot utility, minimum cold utility. Now the point is, at this moment we have not designed a single heat exchanger. We don't know which stream is applying heat to which cold stream, from which hot stream it is going to which cold stream. But we know what will be my minimum hot utility and minimum cold utility and total potential of heat recovery for a given delta T. This is known as the targeting. Okay. Mathematically, we are solving a linear programming problem, but now we have solved completely graphically. Right? You can actually do it in simple graph and you can see the solution. Right? That's the part of it. So that's why this pinch analysis gives the focus on targeting before designing so that you can save a lot of time. Now, if we look, then the question comes is, can we do it using algebra? Because making that graph itself will be difficult. I'll show you quickly. Then you can always look at this paper to find it out. So we'll start with this data. So H1, H2, C3, C4, their inlet temperature, outlet temperature, and MCPs are given. And we assume that there is a delta T mean of 10. Delta T mean of 20 degree. Now, whenever this delta T mean of temperature is 20 degree, we are going to do a simple little bit of transformation. See, when we said these streams cannot be taken up and down, but we can make a transformation that if I take this stream down by half delta T mean and the cold composite curves up by half delta T mean, they are going to touch at this point. Okay? And that whenever two curves touches, their vertical as well as the horizontal distance becomes 0, and we can have a simple mathematical technique to solve them. And that's what we are going to do here. We are going to transform them. So we'll write down all the inlet side here and the outlet side here. But with the transformation, if it belongs to hot, we'll reduce by half of this delta T mean, which is 10 degree. If it belongs to cold, we'll increase by half delta T mean of 10 degree. So the first entry, you can see that it is 175 for H1. You have to reduce 10, it will become 165. Similarly, next entry will be 111. The next entry, now it is a cold stream, so it has to increase. So it will become 30 and 50. Similarly, if I look at the other side, it will become 45 will now become 35, 65 will become 55, 155 become 165, and 112 become 122. Okay, and the MCPs remain same. So this is the first transformation we can do, and then we are going to look at develop a table. So the first entry, this is known as a modified problem table algorithm. Problem table algorithm was originally proposed by Professor Lenov, and I don't know why he called this as a problem table algorithm, but since he proposed that and the name stuck, so we are using it. So that required some drawing. It has been modified, and you can use this algorithm. So first column of this table is writing temperature in descending order. If any temperature repeats, we do not have to repeat that. So now if you look at all these temperatures, then the maximum comes out to be 165. There are two entries for it. So we'll write down 165. The next entry will be 122, this number. Then next entry will be 115 and so on and so forth. So if we write down, it will 55, 50, 35 and 30. Then we are going to write down the MCPs. But now here we have to distinguish between inlet and the demands or the outlets. So inlet, if this temperature comes to inlet, we will take them as positive. If the temperature corresponds to outlet, we will take the MCPs as negative. Now look at 165 is coming here, that means it's plus 10, and 165 is coming here as minus 20. If I add them, 10 minus 20, then I'll get minus 10. For 122, it is here. So this will become minus 15. 105, 15, it is this side. So it's become plus 40. Similarly, continue. 55, it will become 40. For 50, it will become minus 15. Sorry, 15. Here, I just made mistake. This is minus and this is plus. 35 will be here. So this will be minus 10. And then 30 is here. So it will become plus 20. I'm not sure. Is there any question at this moment? Because I can't see the other portal because I'm sharing this window. Okay, let me continue. If you have any question, you just ask me directly because I can't see that all the participant list. Now then we'll do a things called cascading. So what we'll do is I'll first repeat the first one, that is minus 10. And then I'll add diagonally and put it down. So minus 10 plus minus 15, I'll write down minus 25. I'll add these two and write it here. So I'll write down 15. So I'll continue that way. It will become minus 25, minus 10, minus 20 and 0. Okay. Then I'll calculate this entry. The first entry I'll actually write down as 0, just the initialization. Second entry I'll calculate this way. This temperature difference multiplied by cascaded MCP. So 165 minus 122 is 43 into minus 10 will give me minus 430. Okay. So if I continue that way, the next number will be 122 minus 115 is 7 multiplied by 25, I'll get minus 175. So if you continue that way, we'll get these numbers. Okay. I'll come back soon and explain what exactly we are calculating. Now we can do the similar cascading just the way we had done it for here. We'll start with 0 and then we'll diagonally add it, minus 430, minus 605, minus 295, 175, 20 and minus 80. So this number minus 80 comes from that first law balance of QHCU minus QMCU. Okay. Now what we had done, we had written down the temperature, we had written down the MCP of the stream coming in or going out. Okay, and we find out what is the net MCP coming into there. So these numbers are what is the heat requirement or heat available in a temperature interval. Actually, this number should have been written somewhere in between 165 and 122. It doesn't matter. So it essentially says between 165 to 122 in this temperature interval, it requires heat of 430. So minus means requirement, plus means availability. Now what you could do, you see that this is a requirement, a high temperature requirement. We definitely need hot utility. And this is available if you transfer it below to satisfy this requirement, because you can always transfer from high temperature to low temperature. The heat, you can satisfy them. But in mathematically, what we are doing it through cascading, we are saying that assume that 0 is available and I can transfer. So if I start with 0, this is sometimes called invisible cascade, I'll get a negative number, minus 605. And that's not correct, because heat demand cannot be transferred to a lower temperature. It has to come from the higher temperature. That means if I started with 605, this should have been no negative number. Okay. So what I'll do is I just add 605 to every entry. So first one, if I do it, I'll get it 605. Then 605 plus minus 430, I'll get 175. Then next number will be 0. Then I'll get back 900. Then I'll get 775. Then I'll get 625. And finally, I'll get 525. This is the algorithm. And here, now I'm ready to give the answers for energy targeting for a delta T min of 20 degree. I should be able to answer what is the minimum hot utility requirement, minimum cold utility requirement, and the pinch temperature. So if you look at the original, I'll go back quickly to the original data. So here you can see that the steam requirement is 1400 kilowatt and the water requirement is 1320. So the difference is 80. It has to be always there based on the first law difference. Okay, we cannot reduce only one of them. We have to reduce or increase both of them by the same amount so that the difference remains 80. But steam is the main culprit. It's most costly, 1400, and see for how much we have achieved when we have completed the targeting step by algebraic method. Okay, so here we'll just write down the 3 points are important. One is the first entry, 605. That is our minimum hot utility requirement. Okay, so from 1400, we can say that 605 is sufficient. Okay, that means we can make more than 50% energy savings. 525 is the number which corresponds to or cold utility requirement, and 0 is the number which corresponds to pinch point. We have to note this temperature 105. However, you remember that temperature is shifted. So this is a shifted temperature where both the shifted composite curves touch each other. Okay, so that means hot side would be delta T, half delta T up, and cold side will be half delta T down. That means my targets will be hot utility is 605, cold utility is 525, and pinch temperature is 125 and 105. That's the answer we can get. So again, just to highlight, the top of this column, 605 is my hot utility requirement, 525 corresponds to the cold utility requirement, difference is 80, and 0 here gives the point where they touches each other, and that's the pinch point. So what are the insight we can get? We can get that the pinch essentially divides the entire process into two: a high temperature heat requirement zone or heat sink, and a low temperature heat source zone. Okay. And there are 3 golden rules we always use, and this is one of the simple tool that we go for energy conservation in existing industries. No heat transfer across the pinch, or you try to reduce it as much as possible. No cold utility above the pinch, no hot utility below the pinch. If you violate any one of them, you have to have double energy penalty. So in that sense, pinch point is the bottleneck of heat recovery. Can we do something more? Yes, this has been done in the things. We'll start with steam data, we'll generate the composite curves, we'll go for the utility targeting. Then there is a concept called balanced composite curve through which we can target the total heat exchanger area requirement. We can target the number of heat exchangers. So from here, we can make the capital cost estimation. Similarly, from the energy targets, we can find out what is the operating cost. Once you do this, we can actually add them and find out the total annualized cost. We can vary delta T min, we'll get different results, and we can optimize here as a single parameter optimization, and we can see at what delta T mean we are getting the best value. Sometimes this area is not very good estimates. So in many of the cases, it become too complex. So we may not use them, but in that case, we use delta T mean based on our experiences. Okay, I hope that you are not sleeping now. So let me continue. Now the question comes is, can we generalize this concept? Okay. So next half an hour or so, I'll just talk about the generalization, then so that we'll have enough time to discuss or answer your queries. So this is our motivation. Those who work on pinch analysis is by Professor Richard Dawkins. And in his book, The Blind Watchmaker, he says some of the greatest advances in science have come about because some clever person spotted an analogy between a subject that was already understood and other still mysterious subject. Okay, the point here is not to claim myself or my colleagues as a clever person, but the point here is to say that whenever we take one subject and another things we do not know, if we can find out similarities, then it will help us enhancing our understanding as well as in applicability in that different domain. So pinch analysis essentially started from there. Okay, so if we look at the problem that we are talking about, is there are sources which has, every source has a flow F and a quality Q. Okay, you can take flow as the MCP is coming or the heat coming, Q is the temperature. And then there are demands which will take some amount of heat subject to a quality, that the heat has to be higher than, heat coming to this demand has to be higher than this demand temperature. Okay, you can take in that way. So we'll try to transfer the flows from the sources to demand. Sometimes it may not be sufficient, then we need some external source, we call them resource, and that has to be transferred to each demand to meet its quality and flow requirement. All the sources are not utilized. Whatever is not utilized can be actually thrown out, called waste. Okay. So our objective is to minimize resource requirement, and that's the way we can look at our from generalized from heat exchanger network to all other applications. Okay. So these are the different applications of pinch analysis, where flows can be heat, mass, steam, energy, okay, money, benefits, qualities can be temperature, concentration, properties, pressure, CO2, okay, time, profitability, and so on and so forth. So if we are talking about heat and temperature, we are basically talking about heat integration. If you are talking about mass and concentration, we can talk about mass integration, water network, hydrogen network, mass and properties, recycle network, steam, pressure, cogeneration, or we can say energy and CO2, carbon constant, energy sector planning. Okay, and so many of them. Even we can talk about environmental risk, project investment, and these are the years when the first paper came. So you can say 78, 89. So some of them are 2008, 2007. Even this project management came in 2017. So there are a lot of applications are evolving over the time. And we essentially talk about the heat and temperature, that is heat integration approach, because that's primarily from the energy conservation. But in nowadays, we are not just talking about energy conservation, we are talking about all other resources. Can we save them? Can we conserve those resources? So there are many mathematically, if you look at, this is the linear programming problem that we are basically solving through pinch, where this resource requirement, where all these F's are the flows. This is the flow balance for every source, flow balance for every demand, and this is the quality constraints for every demand. So we are basically minimizing resource subject to these three constants, and an additional constant is F cannot be negative. All the flows are positive. It can be solved using different approaches, okay, algebraic and graphical method. So few of the methods which are known as limiting composite curve. Okay, so this is a curve which says whatever will be the requirement, and you take the resource line and minimize to find out a pinch point. It can be source composite curve where you want to minimize the waste requirement, and something like the composite curves, demand composite, source composite, or hot composite and cold composite. You can calculate resource and the waste. Okay, so there are different approaches for these generalized problems. Okay, and there are many modes. So we are going to focus on none of this technique, but just to give you a highlight what is happening in this domain. Some of the applications that we can talk about, this is hydrogen recovery in a refinery. So in refinery, hydrogen is generated in many processes and it is used in many of the other processes. How do you make sure that they are properly allocated so that your total hydrogen bought from outside or hydrogen produced from the hydrogen unit is minimal? It is one of the major things that has been applied in the refinery other than heat integration. Nitrogen recovery is, again, there are nitrogen required at different places. Here you can see these are the nitrogen requirement and nitrogens are coming out from these two places. How much we can recycle so that my fresh nitrogen requirement can be minimized. This is a solvent recovery. There is a fresh solvent is used out here and there is some waste solvent. Then the question comes is, can we reuse this waste solvent, condensate 1 and condensate 2, such that the fresh solvent can be reduced? Okay. In this case, it is the quality is not the temperature or concentration, but the temperature is vapor pressure. And basically the read vapor pressure is used to calculate how much we can recycle. There is a water recovery. So we can talk about in the plant of how much water is required in different operations, what will be the treatment, and how can we optimize the entire water. It has been used in many processes for water requirement. It has been used in isolated energy systems, like where it is not connected to the grid. Those who are from electrical domain can understand this. These are all independent or isolated systems. And so this is for the wind PV system with the reliability considerations. So you can design somewhere inside, but you cannot design an outside if you have to meet reliability considerations. This is a solar thermal system. And again, it is a storage volume versus collector area plot, and you can design somewhere here in between. So typically you'll be designing some close to this portion of the curve. It has been applied to financial problems where there are a lot of projects and there are different funds, and how do you manipulate them or use them so that you'll get the maximum benefit. Okay, many cases even it has been used not purely from the pinch, but also it can use something like non-partially acceptable project. Means either the project has to be accepted completely or rejected completely. It has been applied there with a combination of pinch. It has been used to plan for the healthcare systems. Okay, this kind of representation is known as a grand composite curve in heat analysis or heat integration or heat pinch analysis. You can find out a pinch point. So this is the affordability or affluence index in Kolkata that has been taken, and it has been found out what is happening out there, how many beds are missing. This has been done before COVID. Okay, so based on the data available from the government sites. It has been talked about how can you take care of the uncertainties, because whenever you design a system, we know as an engineer that it will not be final. There will be uncertainties. We have to take care of the safety margins. How do you take care of that? It has been used for multi-objective pinch analysis also, okay, where you have multiple things like cost and water footprint when you are talking about power generations and things like that. How can you do that, a kind of an optimization? So let me go through the concluding thoughts. The first point that I want to make sure is like you understand the philosophy of pinch analysis. So the first point is generalized problem definition. So we talked about flows and qualities. Flows such as heat, okay, qualities such as temperature. But it can be even water or contaminant, hydrogen and purities. So we can talk about different flows and qualities. We are talking about laws of conservations, okay, or laws of thermodynamics. Like energy is conserved, we have used first law, okay. We have also said it has to obey the second law of thermodynamics. Heat has to transfer from high temperature to low temperature. We are taking them. We can use some of the phenomenological relations, design correlations. If we have to estimate the heat exchanger areas, we can use this Q equals to UA LMTD. Or if you say, no, I do not want to use counter current or co-current heat exchanger, I want to use only shell and tube heat exchanger, which is used maximum in the process industries. We can again use the equation Q equals to UA F LMTD. F is the correction factor. We can use that, or you can use some such kind of phenomenological relations to make a better estimates. We are doing some optimization. So the problem that I have presented to you for conservation of energy in a process industry with 2 hot streams and 2 cold streams is a linear programming problem, but I have not used simplex. I have just used some graphical tools so that you can see the solution. Again, I quickly gone through the algebraic methodology, okay, where you can see that we could calculate these numbers through an algebraic way, and the calculations doesn't require too complex a system. Okay, simple pen and paper can solve most of the problems. If your temperatures and MCPs are like with a lot of numbers after decimal places has to be accounted for, you might use a calculator. That's all, or simple Excel or some kind of a spreadsheet. You can see that there is a graphical representation. Through this graph, we can analyze lots of things. And say, for example, when we had gone to do an energy audit for Gujarat refinery, we could identify that energy conservation potential by making some changes. Now, what will happen to those changes, how much energy can be conserved, we can first predict it through this pinch analysis. Okay, we said that some pump around duties, if it is reduced, then there will be a lot of energy conservation potential. We found out what could be. Then finally, we have gone back and done the simulation. It's not that we started doing the simulation multiple times and try to discover it. So we have taken for many practical cases this targeting approach. And this targeting is essentially a prediction of the optimum performance prior to synthesis of detailed design. So what do I mean by that? We have not done a design of any single heat exchanger, but we simply said how much minimum hot utility or minimum cold utility is required. Okay, we can have a lot of physical insight to the designer. So long time back, there was a company approached me and say, can we conserve the cooling water in our cooling water network? So they sent the data, I looked at it, spent 5 minutes, and I say that the potential is only 5%, theoretical potential. So if we do it, maybe we can achieve 3.5 to 4%, but not more than that. Don't expect. So now I probably spent 5 minutes. The company knows now what we expect, what to expect, how much conservation. They should not come that, okay, I have a cooling water circuit and you can conserve 30% of cooling water. No, that's not possible. So we can have physical insight. We can use it as a preliminary screening tools. Okay, we can look for different design alternatives. And it's also a step change of a learning curve. That means if you do an pinch analysis for a company, you need not have to say that every year I can conserve 5%. Because if you do pinch analysis, you know the thermodynamic limit is so much, maybe 30% itself can be conserved in first year, and then next year onwards, you cannot conserve anymore. So that kind of things can be actually done. If you look at the brief history, how the pinch analysis was progressed, this is Budolenov, 1970s, he basically published. During his PhD, he worked with Professor Fowler, and then he joined University of Manchester. That time UMIST, it used to be called University of Manchester Institute of Science and Technology. Later on, it has merged with University of Manchester. And he started this process integration center out there, where at one time 43 industries were part of that uh, department. Okay, and they are funding monies to learn what is happening. Okay, what are the new research design has been done by Professor Burulenov. Then he started his own company called Lenov March. It started in March, and later on he sold that. This is colleague of Professor Burulenov. His name is Professor Robin Smith. In 87, he extended this heat exchange network for batch processes. So that means it's not only for continuous processes, but it can be applicable to even batch processes, where time becomes an important issue. He also extended this water minimization or water pinch in 1994 with his students Wang. In 1989, this is Professor Muhammad El-Halwagi. He works on PhD things, finding out the similarity between heat exchange and mass exchange. Those who are with chemical engineering background or those who are with the chemical engineering department, there is a course called transport phenomena. Yeah, I'm sure all of you know that heat exchanger, mass exchanger, and momentum transfer, heat transfer, mass transfer, momentum transfer have many similarities. So he tried to look at the similarity between heat transfer and mass transfer and came up with mass exchanger networks. He is at present the faculty in Texas Agriculture and Mechanical University, US. He also in 2002 extended this for the property pinch, okay, or property pinch integration, where need not be concentration or temperature. You can use something like I mentioned reed vapor pressure in that solvent recovery problem. These are two colleagues of mine. This is Professor Raymond Tan from Manila, Philippines, and this is Professor Dominic Fu from Malaysia. They came up in 2007 another interesting application called energy planning or carbon constant energy planning or carbon pinch, sometimes it's also called, and how you can design the power systems or energy systems at large where you can conserve for the carbon dioxide emission. 2007 also one extension came from IIT Bombay, which talks about how do you use this principle to design and optimize isolated energy systems, especially important for renewable energy systems. In 2017, with Raymond and Dominic, we worked and then we came up with how do you apply this pinch analysis for financial systems. Okay, so you can see that even 2017, just before the lockdown, we came up, and then still it is going on. There are extensions is happening on different applications every now and then. So when pinch analysis, when I started looking at the process integration, we talked about optimization method and conceptual method or thermodynamics method. So pinch analysis I projected as a conceptual process integration approach. But over the year, it has been developed as a simple and efficient algorithm to with exploiting the spatial structure with enhancing conceptual understanding of the problem. Okay. So we'll try to define this. There is no definition of pinch analysis available. So I tried to define it. Maybe it will has to go through some modifications over the year. So pinch analysis can be defined as a set of systematic and algebraic methodologies with graphical representation for designing integrated production system for sustainable development through resource conservation. Okay, we can talk about various resources or multiple resources at a go with an aim of making sustainable development. The pinch concept has been used in many places like process utility system, which I have just shown to you. Okay, it has been talked about scheduling to strategic planning, improving efficiency, energy as well as raw material utilization, continuous to batch processes to semi-continuous processes, all aspect of the process, reactors, separators, and so on and so forth. If we modify how we can make the energy conservation, how can make the water conservation, and so on and so forth. It talks about integration between different processes, wastewater minimization, emission reduction to pollution prevention, hydrogen management, especially in refineries, aggregate production planning, sizing renewable energy systems, and the list goes on and on. Recently, we came up with Dominic, Raymond, and myself came up with this journal, Process Integration and Optimization for Sustainability, focusing on not only pinch, but also process integration aspects, methodologies, and all. There is the last 4 years, from 2017 onwards, we are running this journal with a lot of enthusiasm. So even I welcome all of you. If you are doing some research related with optimization and sustainability, you can submit to our journal. So pinch analysis evolved over the time. From it has started as a thermodynamic tool for heat exchanger network, and I'm sure through example I could demonstrate that it has gone into a different level where we can talk about system level optimization. Application also improved, okay, and evolved over the energy efficiency improvement to conserving resources. It is applicable directly to industrial problems, so that's why now it has been what people are working in academia as well as in industry. We can see only the results and the papers coming from academia. Unfortunately, we do not see that many papers coming from the industry except in few conferences. It is applied to various industry. You just name them: food, paper, dairy, whiskey, cement, specialty chemicals, bulk chemicals, petrochemicals, oil and gas. In fact, in the refinery sector now, if you there are certain process plant, when they come up with the requirement, when they advertise, they say basically that you have to perform the pinch analysis. Research potential is also significant. I hope that you have not really slept. So this is probably another cartoon way of defining pinch analysis. Now this is important, especially from the COVID perspective, that we are just going to feel a little pinch, then a horrific burning pain. Your eyes will roll back into your head and you'll drool uncomfortably. If that kind of feeling is happening to you, then I'm probably successful in giving a talk on pinch analysis. Okay, uh, okay, let me finish this with one of my favorite poets from Gujarat, Narayan Hemchandra. And this particular quotation is coming from Mahatma Gandhi's book, My Experiments with Truth, where he said, great men never look at a person's exterior, they think of his heart. In some extent here, not the main, but we are looking here through some curves and all, much more beyond what the optimization says through representation. And that's probably inspired me to look at the pinch analysis. Okay. So that's all from my side. We have roughly 40 minutes left, but we can definitely discuss if you have any question.
So if any participant has any question, he or she can ask this, sir.
Thank you, Dr. Giri.
Sir, I want to ask some questions. Is this technique been used in some analysis softwares like ANSYS, Fluent, etc. In mechanical engineering field currently?
Not in Aspen, not in ANSYS or Fluent, but Aspen uses it. Aspen is a process simulator, uses the basics of heat integration. Okay, it's called Aspen Energy. So some preliminary calculations can be done about the heat integration through Aspen.
Okay. And sir, it has been merged with some other kind of techniques, parallel techniques, and has been applied in the field for calculating different parameters.
See, now that's what I'm saying is a tender document for refineries, even in the Indian refineries, uh, will say that you must do pinch analysis. So some of the industries, it has really gone into that, that it's now calling in the tender part. Okay, tender document is coming specifying pinch analysis, but it has been used in all sorts of industries. Okay, so you just name an industry or type of industry that has been used worldwide.
Okay, sir. So, is there any other participant who want to ask the question? Okay, so now we are moving towards end of this session. So, uh, thank you very much, sir. Dr. Santanu Bandyopadhyay, sir, has nicely explained all the aspects of pinch analysis approach and has started from the scratch that when it was rather invented and when it was used, and in fact it has been used till date, and he has discussed the different energy conservations management and means difference between energy management and analysis and conservations, and aspect of pinch analysis approach and optimization techniques, and he has also compared the pinch analysis approach with somewhat familiar other approaches, and he has also shown us the history of this pinch analysis approach, which was the way in which it was invented, and he has also nicely given the example that how it can be applied to one real life problem in some specific situations. So I think, sir, from your presentations, the person who is interested in this domain will has definitely got a very valuable knowledge and informations, and this session will definitely help those who want to pursue the research or propagate the research in this field. So again, on behalf of BNB Institute of Technology and all the participants and committee members of the STTP, I thank you, Dr. Santanu Bandyopadhyay, sir, for accepting our invitations and for delivering such a nice and versatile session, sir. Thank you very much, sir. We have enjoyed the session a lot, sir.
Thank you, sir, and thank you to all of you. And again, I request to stay safe. There is a difficult moment. Again, we are facing the third wave. And Happy New Year to all, as well as you and your family members. Thank you very much.